So today we shall start by defining isomorphism of graphs. That means, given any two graphs, what do you mean by that the graphs are isomorphic? Okay. So what is the definition? So let us suppose that two graphs are given, G1 V1 U1 and G2 V2 E2. Be two graphs. Then they are said to be isomorphic. They are said to be isomorphic if one can find out a 1-1 correspondence, phi from the vertex set of the first graph V1, that is V1, to the vertex set of the second graph, that is V2, such that the map phi will preserve the adjacency of two vertices. That is, such that if you take such that UV belongs to the edge set E1, if and only if the vertex U goes to phi U, if the vertex V goes to phi V, then you see that this will be an edge in E2. Okay. That means if U and V are adjacent in the first graph, then their images are also adjacent in the second graph. Okay. কি কৌশি কি ঠিক আছে শুনতে পাচ্ছ তো? So that means the map phi from B1 to B2 will be satisfying this property that UV, if UV is an edge in the first graph, then their images, that is phi U and phi V, they will be connected through an edge in the second graph. Okay, so that means the map phi will preserve the adjacency of the vertices amongst the two graphs. Okay. Okay. So that is phi preserves the adjacency of vertices in between the given graphs. Okay. And if two graphs G1 and G2 are isomorphic, then we denote it by G1 is isomorphic to G2, equivalent to G2. Okay. For example, suppose we consider a graph like this. Okay, and they are connected. Yeah. So here you can label the vertices, so v1, v2, v3 and v4, and this is your graph g1, b1, e1. Okay, and suppose you take another graph with 4 vertices. Okay, so these are 2 graphs. So this is your g2, b2, e2. Okay, so now we are going to set up a 1-1 correspondence in between these 2 graphs through and 1-1 correspondence between the vertices of the first graph and the vertices of the second graph. Suppose it is your u1, u2, u3 and u4. So what you do, you just define a map phi from b1 to b1 to b2 by, so phi of v1 will be mapped to u1, phi of v2 will be mapped to u2, and phi of v3 will be mapped to u3, and phi of v4 will be mapped to u4. Okay, and then you see that, so this phi, so phi is a bijection, right, by definition. And if you check, suppose you take any 2 vertices who are adjacent, that means suppose you take v1, v2, right. So this edge, so v1 and v2 are adjacent in the first graph, and their images are, so v1 goes to u1, that is, it is your phi of v1, and what is v2? v2 is your u2, phi of v2. So here you see that phi of v1 and phi of v2 are also adjacent. Okay, if you take any, suppose you take v2, v4, then this v2, v4 means, so this is your phi v2, and what is v4? This. So these are adjacent. So you see that, so firstly this is true, and secondly phi preserves the adjacency between adjacent vertices. That means, so hence phi is an isomorphism. Okay, from G1 and G2, from G1 to G2, that is G1 is isomorphic to G2. So these 2 graphs defined above are isomorphic. Okay. Okay. Now I can give you 2 examples, 2 problems. So you need to check that these 2 graphs are isomorphic. Okay, this is one graph G1 and another one. So we consider this graph, and here you have another graph. Suppose yeah, okay. So check whether these two graphs are isomorphic. Okay, and another problem I can give you. Suppose again you consider the same graph as above. Okay, and another graph is like that. Okay, so check whether they are isomorphic. Okay, okay. Now it should be noted that if we consider a class of graphs and then the relation of being isomorphic amongst graphs or being isomorphic on this class will be an equivalence relation. Okay, okay. Now let's define okay, okay. Now let's define another nice concept of degree of a vertex. Degree of a vertex in a graph. That means the number of edges that are incident to that vertex. That means if you take a graph and if you consider a vertex, then how many edges that are incident to that vertex. So here it is 3. So if you take this, if you label this vertex as V, then the degree of that vertex is 3. Okay. So okay, so in general, so the degree of a vertex V in a graph, suppose you take GV will be defined to be the number of edges that are incident to it. Okay, that are incident to it, and if the graph will have a loop, then we are to add two to the number of other edges that are incident to that vertex. Okay, that means if you have a loop, suppose you take and here is a loop, then what will be the degree of V? The degree of V is 1, 2, 3, 4, and here for this loop you need to add 2, that is 4 plus 2 is 6. Okay, so for any graph GV, the degree of a vertex V will be denoted by dV. Okay, okay. Note that if you see that in a graph you find out a vertex on which there is no edge that are incident to it, okay, then that vertex is called an isolated vertex. That means a vertex, note that a vertex in a graph of degree 0 will be named as isolated vertex. Okay, okay. Also in a graph GV, the cardinality of V, the vertex set, is called the order of the graph. Is called the order of the graph, and the cardinality of the edge set E is called the size of the graph. Okay, yeah. Now in this context, a vertex of degree 1 is called a pendant vertex, or one may say that it is a leaf, a vertex of degree 1. Okay, that means if you take a graph, suppose this one, and here you take this vertex. Okay, so this vertex is a pendant vertex, that is of degree 1, and this vertex is an isolated vertex. Okay. Okay. Now we will have a theorem, which is, so for a graph is a very important theorem. For a graph GV, you will see that if you take the sum of the degrees of the vertices, then that will be an even number, that is, it is the twice of the number of edges, where E being the number of edges in the graph. So this is a very nice theorem, and we will prove it later. Okay, that sum of the degrees is actually twice the number of edges in the graph. And if you assume this result for the time being, so you will see that so suppose you take, for example, suppose you take a graph okay, so then suppose this is your V1, this is V2, this is V3, V4, and this is V5. Then what is the sum of the degrees? So what is dV1? Is 1, 2, 3. So it is 3. What is dV2? 1, 2, 3. What is dV3? 1, 2, 3. What is dV4? 1, 2, 3, 4. And what is dV5? Simply 1. So the sum of degrees is 3 plus 3 plus 3 plus 4 plus 1, that is 9 plus 4, so it is 14, right? So that means it should be 2 into 7, right? Okay, so how many edges you have? 1, 2, 3, 4, 5, 6, 7. So this is 2 into E, where E the number of edges. Okay. Okay, and assuming this result, you can at once prove that the number of odd vertices. What does it mean by odd vertices? The vertices having degree odd. Okay, so the number of odd vertices in a graph is always even. Okay, so odd vertices means it is a vertex of odd degree. Okay, so what is the proof of this corollary? So recall that sum of dv is 2e, which is even, right? And now let, if you partition the set of all vertices respectively by two disjoint sets, that is, one is VO and another one is VE, where VO means the set of vertices in the graph having degree odd, and VE be the set of vertices having degree even. Okay, okay. So here you can partition the set of all vertices into this two disjoint sets. Okay, so note that these two sets are disjoint. So therefore you can separate, you can split this equation, this sum, into two parts. So we see that sum of dv, v belongs to VO, plus sum of dv, v belongs to VE, equals to 2e. That is an even number. Okay. Now since this V is a set of all vertices of even degree, so their sum must be an even integer. Now clearly sum of dv for V has been taken from capital V must be even. So therefore, so hence the sum of the degrees, sum of the vertices of odd degree will be even, since the sum of even number of odd integers is even. Okay. So this implies the cardinality of V naught is even. So this proves the theorem. This proves the result. Okay. Okay. Now let us define some new concepts which will be prompting us to define the connected graphs, okay, using this notion of paths, walks, closed paths, cycle, etc. So what does the mean? So they mean that, so suppose you have a, so let GV be a graph. So what do they mean? So a walk of length k. So you are defining the first concept in this regard, which is a walk of length k. What is that? This is a sequence. This is a sequence of vertex and edges. Okay, this is a sequence. So you take V0, and V1 will be connected through E1. So I put it in the middle. Then V1 and V2 will be connected through E2, and then E3, then Vk minus 1 Ek, and it is Vk. So this is a sequence of vertices and edges in the graph GV, such that, what is the condition that will make it a walk? That is, if you take EI, then it will be an edge in between Vi minus 1 Vi. Okay, so any sequence of this form will be defined as a walk of length k, and it should be noted that in a walk, a vertex may be repeated, an edge may be repeated. Okay, so vertex or an edge may be repeated. May be repeated in any number of times. Okay, now a walk of length k will be denoted by V0 to Pk. Okay, for example, suppose you take a graph okay, you take this graph and you label the vertices as the natural numbers 1, 2, 3, 4, 5, 6, and the edges in terms of the alphabets, small letters, there is small a, small b, small c, small d, small e, small f, small g, small h, small k. Then you can consider this sequence, which will be started from 1, that is 1, then you take the edge b, so it is 6, and then you take the edge D, so it will go to 5, and then it is E, it will go to 2, then it is 5, then it is F, so it should be 3, then it is G, so again you come back to the same 5, same vertex 5, and then it is K, and it finishes off at 4. So this is going to be a walk. Okay. So this is the first definition. Secondly, we are going to define a trail. So what does it mean? A trail is nothing but a walk. A trail is a walk, is a particular walk, which will satisfy that a walk with no repeated edge. Okay. Thirdly, we define a path. So a path is a walk with no repeated vertex. Okay. So path is a walk with no repeated vertex. Now suppose you take two vertices in a graph, U and V. So we define that what does it mean by a UV walk? UV walk. Okay. So a UV walk is a walk which has U as its starting point, as its first vertex, and V as its last vertex. Okay, and these are the end points of the walk. Okay. Okay. So suppose you take any two vertices and you are considering a walk, and this U and V will be their end points of that walk. That is, U will be the first vertex and V will be the last vertex. Then it is called a UV vertex. A closed walk is a walk of length at least 1. A walk of length at least 1, and its end points should be equal. Its end points are same. That means you start from U and then you come back to the same vertex U. Okay, so that is called a closed walk. Along this line, you can define a closed path. What does it mean by a path? A path is a walk with no repeated vertex. And what does it mean by a closed path? That means their endpoints are same. Okay, and there are no other repeated vertices in the path except those endpoints. Okay. And in that case, a closed path is actually will be defined as a cycle. Okay, will be called a cycle. So a cycle is defined to be a path having the endpoints as the only coincident vertices. That means we are defining this as a closed path. Okay, and since the path has no repeated vertex, but whenever you are defining a closed path, so then you will come across the situation where their endpoints will be equal. You will come back to the same vertex. So that is why this will be named as cycle. Okay, that means suppose you take a graph this, so then this is suppose v1, v2, v3, v4, v5, e6, and this is e1, e2, e3, e4, e5, e6. Okay, so you can take a cycle, suppose v1, e1, v2, e2, v3, e3, e4, e4, v5, e5, right, v6, e6, and again v1. So this is a cycle, because except those endpoints there is no other repeated vertex. Okay, now it's time to define what does it mean by a connected graph. Okay, so graph is said to be connected. So what is the intuitive idea of connected graphs? That is, what I feel is that if you take any two vertices, then they can be connected through some walk, right? So this is the definition of connected graph. That is, a graph GV is called a connected graph. A connected graph if for any two vertices u and v of the graph there is a UV walk. There is a UV walk in the graph. Okay. So if you take any two vertices, then there should be a walk in between these two vertices, and otherwise it is called disconnected. It is called a disconnected graphs. If you look at this graph which has been pictured above, so this is a connected graph, right? If you take any two vertices, then they are connected through some UV walk. Okay, and you can also draw some other graphs with your own. That is, if you take any something like that. So these are connected graphs. Okay, so this is a connected graph. If you take this one, so this is a connected graph. If you draw some triangle kind of graph, so this is a connected graph. But if you take them together, that is, this is one piece and this is your one piece. If you take these two graphs all together, then they will be disconnected, right? Because in between these two vertices, this one and this one, there is no UV walk, right? So therefore, altogether they are disconnected. Okay, so if you take any 2 or 3, 4 connected graphs, so if you take them all together, they will give you a disconnected graph, and then that connected graphs, that connected subgraphs of that original graph will be called connected components. That is, for example, if you take these two graphs together, then each of them will be called connected component. Okay, so here is our next definition, that is called component. That is, we define it as a maximal connected subgraph of a graph, of a disconnected graph. Your graph should be disconnected. If it is connected, then it is the only connected component, right? So of a disconnected graph is called a component. Of the graph. Okay, so in above, so together these two graphs will form a disconnected graph in which each of them is a connected component. Okay, okay. Okay, so let's prove a result in this context of connected graphs. That is, suppose you take, so let G be a connected graph then it is true that every UV walk, now in a walk you will have two cases. There may be a possibility of repeated vertices, there may be a possibility of repeated edges. Okay, but if you think of paths, then you need to construct a sequence of vertices and edges where you will see that there is no repeated vertices. That means any UV walk can be transformed, can be used to define a UV path. So every UV walk in G will have a UV path. Okay, so in between these two vertices you can generate a path using that walk. Okay, that means you are to cancel out those repeated vertices. Okay, so that is your job. So let's prove this theorem, and we will prove this theorem through induction on the length of the work. Okay, so we use induction on the length of the work. Okay, so let L will be denoted by the length of the UV work. Okay, now if L is 1, then the work itself is a path, right? That is L is 1, that means this is your U, this is your V. So that is, there is only one edge and there is no possibility of repeated vertices. So therefore this is a work, this is a path. So then this is a path itself. Okay, and the theorem is true. Okay, okay, now let us assume that the theorem is true when the length of the work is less than L. Okay, so we are assuming that the theorem is true for any UV work of length less than L, and we now prove the theorem for a work of length L. Now consider a UV work of length L. Okay, so you can write down the work, you can denote the sequence like this way, that is your, this is U and this is U naught, and I will omit the edges and I just write down the vertices, because if you take any edge, suppose you take UI, EI, UI plus 1, so that means you can denote this edge as UI, UI plus 1. Okay, so that is why we can adopt this idea and we will write down the UV work in this way, that is U naught, U1, U2, UI, again UI, okay, UL. So this is your V, right? Now as you see in this work, we have considered a repeated vertex which is UI. Okay, there may be others, but for that case we just consider that this UV work has the repeated vertex UI for the time being. Okay, so here UI is supposed to be a repeated vertex. Okay, then what you do? Okay, so now if you look at the work, then you will see that you can split the work into three parts. One part will be taken from U naught to UI, another part will be taken from UI to again the repeated UI, and then UI to UV, right? right? So here you denote W1, the portion of the work from U0 to the first occurrence of UI, okay, and then you denote W2, that means the second portion, that is the portion of the work from the first occurrence of UI to the last occurrence, okay, of UI, because we have assumed that. So maybe in between this UI to UI there may be another UI, but we are considering that this is the first occurrence and this is the last occurrence, and in between we just ignore that part, okay. We will consider that portion starting from first occurrence of UI and which runs over up to the last occurrence of UI, okay. And then we denote W3, the portion of the work from the last occurrence of UI up to UL, that is V, okay. Okay. So what we do? So if you draw the segments, these portions, so this is your U, that is U0, and this is your UI, the first occurrence of UI, okay. So this is the portion W1, and then I would like to make it a loop like thing here. So this is your W2, okay, because through this work you just start from UI and come back to UI again, because UI is the repeated vertex, and then it runs over up to UL, that is V, right. So what you can do is that you just consider the work that is W1 union W3 by removing W2. From the original work, and you will see that this resulting work is again a work from U to V, but in this work the UI will never be repeated, right. So okay, now this work, since we have omitted this part, so the original work was of length L, so that means by removing W2 you have settled down that the resulting work must be a work of length less than L, right. So this work is a work of length, I should write it as UV walk is a UV walk of length less than L, right? Now you have assumed already that the theorem is true for any walk of length less than L. So that means by the hypothesis, so by the hypothesis, this resulting UV walk, that is your W1 union W3, W1 union W3 has a UV path, right? Has a UV path. Okay, which is clearly contained in W, right? And this completes the proof. So I'd like to stop.